Good morning, ladies and gentlemen. Today is Tuesday, April the 7th, 2020. Welcome to Remote Learning with Mr. Chen. This is for our grade 11 functions 11 university students, MCR3U. And I just wanted to start off again, hopefully you're all healthy and you're all safe, and we're dealing with a lot of issues at the moment, and we're trying to get you successful by continuing on your math journey. Couple things I need to issue in no particular order. Hopefully you've got a chance to check the Google Classroom and got a chance to download for today the related PDFs that we're going to be talking about today. Second of all, hopefully you got a chance to know my email address. It is nt.rchen@gmail.com, or you can email me at Raymond, that's my first name, RAYMIN, .chen, CHEN, at tdsv.on.ca. At any time through the video, please feel free to pause the video. It's my first time really doing this, and I just want to make it joyful for some of you that you're trying to learn at home, which leads me to maybe any anxiety issues. Anytime I feel for you as a student going through this rough time and trying to adapt to your learning, and if you are worried about certain things, please feel free to contact your North Toronto guidance counselor or contact me if you have a problem about some of the issues here. So finally, I want to let you know from the Google Classroom, there are some nice mathematical resources that you can refer to. Clearly, one is your handouts that we've given to you. Number two, there's the CEMC sponsored by the University of Waterloo that have some really neat links, and I'll try to provide that for you. Of course, you can actually use your textbook. And finally, also myself, these videos that will help you. In terms of the assessments, we might have some exit cards coming up, not for this first one, but we might have some exit cards that just making sure you follow along through the video. And there might be a culminating, like a quiz or an assignment or something at the end that we'll ask you to kind of digitally hand in. I'm not too sure, so hang tight. And let's just get through the content, okay? So really quickly, today, there's going to be probably a lengthy video on two concepts. And we started off before March break on looking at the introduction to this unit called periodic phenomena. And what we're going to be doing two things. First one is, again, introduce the graphs of y equals sine x and the graph of y equals cosine x. The second part is actually introduce periodic phenomena, its definition and terminology. I'm now going to switch over to share the screen and see how we're going to look at our PDF documents. Here we have is the handout of what we're going to be looking at, investigating the function of y equals sine x. And again, if you need to pause the video, feel free to just check what's happening. I do apologize. I am recording from home, and so my dog might be barking, or you might hear some weird sounds. So hopefully I can pause the video if something goes wrong. I'm also using a writing tablet, so I am not 100% familiar with it, especially to pause the video, so please bear with me. So what you see from here is a table, and we did something like this in class, although not exactly the same one. This is an alternate one that I found and managed to use. And what we're going to be doing, just like with trigonometry, we're going to actually find the ratios when we evaluate. So again, pause the video and feel free to use your calculator. Make sure it's set in degrees and actually evaluate. And notice this handout says round the decimal values of sine x to the nearest tenth. Maybe what we're going to do is round the values to the nearest thousands. So maybe thousands. Okay. Hopefully these are the answers you got, and I'm going to do this right now. So the table is, again, an exploration of what's happening. And notice we're going from 0 to 360 degrees, which is actually the unit circle. Hopefully you can read my handwriting. That's 0.866 and 1. Some of you realize actually the related acute angle is actually 30 degrees for a lot of them. Not at 180 though, that's 0. I made a mistake. Glad you realized already we're in the quadrant of 240 degrees on the unit circle. And the ratio for sine should be negative, because you kind of already done this already when we were looking at the cast rule. So some of you are slowly going to make a connection to what we've been looking at. So what we're going to be doing right now is actually plotting these points. On the x-axis is our values of x, degrees, and our range is going to be on the y-axis, right? Which is our ratios. So hopefully, again, if you have to pause the video, feel free to just check and see if you can plot. Here we go. I'll plot the critical points. And I missed for some reason. Yikes. It's not racing problem. And obviously I don't have my scale all labeled out. And so let's make sure we're okay. That's 180 degrees. That's 270. That's 360. So now we got to make a nice curve. Just make this a little bit thicker. And try your best. And what you're seeing, hopefully, as you go through the critical points here, it looks like oops. Looks like a nice wife. I'm probably better on the freehand rather than on the grid. So that's what the y equals sine x graph looks like. A couple of things you're noticing, it looks like a wave. And you would be correct. The word that we're actually looking at with the periodic phenomena, not all of them, but in this case, is this word called sinusoidal. It's based on the word sine. And so when we see waves like this, that's how we use it. There's a couple of things that we can actually introduce in our terminology. First of all, it's going to be connected to our actual handout. What is the maximum value of your seeing of this particular wave? Well, the maximum value happens to be 1. And what's the minimum? Well, it happens to be -1, right? So we can fill out this table. What is the domain for this? For all x values, it seems to be no discontinuities, so the domain is actually x belongs to real numbers. And the range, it goes from -1 to +1. These two words, period and amplitude, we haven't talked about just yet, but we'll introduce that in a moment. The y-intercept, I think everyone agrees. Let's just emphasize that really quickly. This particular y-intercept, notice, is actually right there. And so the sine graph actually starts at 0. So some students kind of know that. What are the x-intercepts? And again, a lot of you realize what I'm going to be doing. The x-intercept seems to be appearing at there, there, and there. So it's actually 0 degrees, 180 degrees, 360 degrees. And then every next 180 degrees. A lot of you actually know what I'm doing. This, what we've graphed from 0 to 360, believe it or not, it's classified as one cycle. One cycle. And we'll explain this again in a moment. But what is the length of this cycle? Well, this cycle starts at 0, and it goes all the way to 360 degrees. And that's what it's called. It's called the period. So the period has to be 360 degrees for the sine graph. What's the amplitude? This is the new terminology for today, and I'll use a different color. The amplitude, visually from a graph, it is actually the distance from the maximum to the horizontal line there. And I'll use amp. In this case, the amplitude happens to be a value of 1. There's another way to calculate it, which will show you a formula on the next handout, but that's what we have so far for the sine graph. So these are some traits that you're supposed to recognize. Now, why am I connecting it with cos and the unit circle that we already talked about in our previous trig unit? Let me just show you with a sketch over here to the side so that hopefully some of you will see a little easier. I'm going to kind of trace the unit circle. Remember where the radius is actually 1 unit. And again, I'm going to go into a counterclockwise fashion. But watch what I'm going to do as I trace this out. Really, the sine graph is actually the unravelment of the unit circle. And I'll show you hopefully by explaining it. It's supposed to be green. And so what I've drawn on below is the unravelment of that unit circle going in a counterclockwise fashion. Specifically, this point here is 1, 0. This point at the top, which is 90 degrees, is 0, 1. And this point here is -1, 0. And this last point is 0, -1. And what do they entail? Well, we didn't really talk about it in our unit because in grade 11, it's too much information to go through. But basically, the units that we have there, 1, 0, 0, 1, -1, 0, represents the angles at 0 degrees, 90 degrees, 180, 270, 360 degrees. And so a lot of you actually noticing what is happening. At 1, you see this pattern actually continue. At 180, it's at 0, and we keep on going. And in fact, the whole idea about this unit is first understanding that the next pattern. So a lot of you realize, if I were to continue this pattern, and I might not give myself enough room, what color would be the next color if I were to keep on going in this counterclockwise fashion, right? Kept on going in this direction. Well, I think a lot of you understand the next color, if we kept on unraveling, would be blue, right? And so this pattern repeats. So basically the definition that we're looking at for periodic phenomena is patterns that repeat. And since today is Tuesday, April the 7th, our week is a good example of periodic phenomena. What do I mean by that? Well, tomorrow is going to be Wednesday, and then the next day is going to be Thursday, and then coming up is Good Friday holiday, called Good Friday, and then the weekend is Saturday. These patterns repeat. We also have another good example in chemistry. It's called the periodic table of elements. And basically the groups of the elements are actually grouped in how their properties lie, like the alkali metals. Finally, at North Toronto, again, the reason why we call periods at our school is because those patterns repeat. So we have at North Toronto run on a day 1, 2, 3, 4 schedule. Although of course, things like this pandemic has caused us an upheaval. So I understand we're not going through, we're just trying to adjust. With periodicity, we can actually make good predictions. And this is what we're kind of learning. If you need to learn more, please feel free to pause the video and refer to your notes and to the CEMC handouts or CMC connections that I provided for you. But we're going to move on to the next handout. I'm going to speed this one up just a tad. And I'm not going to do the unravelment for the cosine graph, although I did mention it. And again, in your handouts, you might see it now because when we photocopied them before, they were all in black and white. But the ones that we give you now, what I'm giving you now from my previous head of the department is from Dr. Chen, and you can clearly see the colors. The links might not be all true, so just bear in mind they might not exist anymore because they're quite old. But the ideas are still there. Here we go with cosine, really straightforward. Again, if you need to pause the video, feel free to. I'm gonna use a different color this time. And I'm gonna use red. And again, hopefully you're doing this with me, just copying it out. Hopefully you're taking out a calculator and you're evaluating these, but this should be pretty easy. It's because a lot of you actually understand the relationship between sine and cosine. And again, I went to the nearest thousandth. Hope that's okay. So don't feel bad if you didn't. You're just trying it yourself. Maybe some of you don't even need the video. But I do encourage you to kind of do this because for next year in advanced functions, if you decide to take that course, you're expected to kind of already know what these graphs are. And that's why the functions that you've seen were important. Notice with the cosine graph, when you start plotting this one out, notice where it starts. At 0 degrees, that value is actually 1. And at 30, 0.866, 60 degrees, 0.5, and then 90 degrees at 0. And then 120, which is the next one, is going to be negative 0.5, and then 150 is negative 0.866, and then 180, it's right there. So let's put that 180. And then 210 is negative, and then 240 is negative 0.5, and then 270, let's put that number there. And then 300 is 0.5, 0.866. Apologize for my handwriting there, ladies and gentlemen. And then back to 360. So notice some of you are actually kind of making sense of what we're doing. The cosine graph looks almost exactly the same as the sine graph. And so, again, this is y equals cosx. First of all, it starts at a max, not at 0. So that's a couple of things that we kind of need to worry about. And it starts at 1, right? So a lot of you already noticed that some of these answers already. The maximum value is still 1. The minimum value is still negative 1. The main is still x belongs to all real numbers. And the range, notice these are all the same as the sine graph. What's the period? Again, what we're asking you to do is graph the whole distance of one cycle. And again, I really haven't explained that, but we'll talk about that in a moment. Of this whole distance here. And that length is actually 360 degrees. Notice again, I'm going to do this one just a little differently. What's the amplitude? The amplitude, this time, notice I'm going from this horizontal, but I'm going to go to the minimum. What is that amplitude? Notice it's still 1 unit. So that's that length. It's the absolute value of that. What's the y-intercept? Again, a lot of you notice what I'm doing right now. It's that value there that I've circled tremendously. And that value is 1. There is only one y-intercept. But what's the x-intercepts? I think some of you actually can see this. And it happens to be 90 degrees and then 270 degrees. And then notice it's every next 180 degrees. I'm not going to unravel the cosine graph, but a lot of you can clearly see that if I were to sketch both of these graphs, and let's just change the color here so we get the colors. And I'm just sketching. So I think I use blue for sine. So that's the sine graph. And the red graph is the cosine graph. And some of you realize these are both sinusoidal functions. And in fact, if I were to take the cosine graph and continue going backwards, continue this one, go backwards. Some of you are kind of understanding already the idea of transformations of functions, right? The sine graph seems to be like the cosine graph, but shifted left a certain number of degrees. Hopefully you've managed to see what we're doing now as I switched over to the handouts. And again, this is trigonometric function periodic phenomena. Just give me 1 second. So these are good examples of what we're looking at. Motion of pendulum swings back and forth, and you can see there's a sinusoidal graph for that. These are basically springs. They're called the undamped and damped oscillator. Again, those links may or may not be there. Your heartbeat is also a really good example of a periodic phenomenon. Although not true sinusoidal, it's nonetheless periodic. If I keep on scrolling up, these are their classic ones. And in fact, I actually like this one over here. And let me just annotate so you can see it. This one is clearly a good one. We'll try to explore that one more in detail. The hours of sunlight. A lot of you actually are doing something innately, even though I haven't prompted you, but a lot of you are actually kind of drawing a horizontal line that would cut that hours of sunlight graph in half. I mean, if you have to zoom in or pause the video or look at your handout more in detail, you could see it. And I think some of you would actually draw the line roughly right about there. Apologize for my not straight line. We'll talk more about this black line that I've drawn, but a lot of you actually doing that are ready for a lot of the sinusoidal functions, even with this ocean tides. And I think some of you, or maybe would argue, Mr. Chen, I would split it down there. Also a good example of periodic phenomena are these sound waves that a lot of you have seen before, maybe in music, and maybe some of you are interested in music a lot and you take it like the equalizer, right? Finally, the Ferris wheel is a classic one. We'll talk more about that in detail. And the phases of the moon, light itself, water waves. These are all good examples of periodic phenomena. So what we're going to be doing now is talk about some terminology. And I'm not going to read them to you, but I think I should highlight some things for a lot of you. So first of all, a periodic function is a self-repeating graph, and the y values of the function repeat at regular intervals. In function notation, if there's a positive p-value, such that f at x plus p, for the function, for every x in the domain of the function, the smallest value of p is called the period of that function, and we'll see that in below. So in this example here, you can see Dr. Chan has provided you a periodic phenomena. It's not true sinusoidal, but it is waves. Maybe it's sinusoidal. We'll talk more about that in a moment because it might be confusing for some of you. And you can see in purple, you can see, no, I'm not annotating. My apologies, I was probably checking the wrong. You can see here, that's the period. And notice the period, you can take any 2 points that shows the pattern that's repeating. Meaning you could take definitely this maximum and that maximum, this minimum, and that minimum. Notice that's the period. And the cycle is the smallest complete repeating pattern of a periodic function. So notice in this above example, the period happens to be approximately 6.28 units. And it's just the length of that repeating pattern. So one cycle. So there's many cycles occurring here. In fact, if I were to count how many cycles, starting here, that's 1. And then that's 2. So there's our 2 patterns, and then there's a third one. That's 0, sorry. Some other terminology that we've used or looked at already is the maximum, and this is known as the peak or crest. The valley, we'll change up my marker here, or trough, that's what they use, or minimum, those are all the same thing. And remember that black line that I drew way back, let's go back here, where the hours of sunlight and the ocean tide? Well, that's exactly the same thing as what's called the equation of the axis or the midline. And notice that there's a formula that we can use. So I sometimes use this called the EOA, equation of the axis. And it's a formula that a lot of you actually innately look at. And in this example, you can definitely use this formula where you take the maximum plus the minimum and divide it by 2. And so in this example, notice how we write it. It is y equals 3. So let's just take a step back really quickly. And I think some of you actually understand what we're doing here. What's the equation of the axis for this one? Again, if you have to pause the video and make your answer yourself, or even look at your handout, I think a lot of you would say that the answer is for this one is y equals 12. And what's so special about that? Well, just recently in March, we had this event called the spring equinox. What's so special about the spring equinox? That happens to be the exactly same amount of daylight hours as there are in nighttime hours. And we represent it special because that's the first day of spring. So this happened actually maybe a week or 2 ago. So you can see clearly maybe right about there, Maybe slightly higher up. Day 400. That's not right. Day 97 or 98 or something. The reason why I bring up 97 is because the 97th day happens to be roughly around March. Back to this. How about amplitude? Now, let's get rid of this. Amplitude, we talked about it, is the half the distance between the maximum and the minimum. Some of you actually saw me do it visually, right? And so that's why you see in Dr. Chan's handout, he used green. So notice he went from the maximum to the equation, the axis or midline, or went from the minimum also to the midline or the equation, the axis. But some of you find this equation a little bit easier, where it is the amplitude is the maximum minus the minimum, all divided by 2. So there's our terminology that you need to kind of know. Finally, we have some questions here, and I think you can actually do this on your own. It shouldn't be too difficult. Basically, for question 1, determine whether each function is periodic. If a function is periodic, estimate its period and its amplitude. Now notice, a lot of these graphs are not in degrees. That is why we had to teach you the radian unit. Very first question, first of all, let's just do this one together. Clearly, we see the patterns repeating, and I don't think it's too difficult. So this is clearly periodic. And what is its period? So taking one cycle, going from there to there, it's really hard to see. It doesn't really have any numbers, but I would say the period is actually going to be equal to 2 pi. Right? So let's see if you guys can keep on going yourself. And their answers are located here. Let's do question 2a though together. Sketch a graph of a periodic function with a given period and amplitude. Now, it doesn't have to be a wave, but most students find it easier as a wave. And the amplitude is 4. So this is open-ended. This is not the only answer. Period has to be 6. Amplitude has to be 4. So I'm going to take a sinusoidal one, sketch it out, right? And notice, I'm going to make that 4, make that 0, make that negative 4. Because again, the equation of the axis has to be exactly the same. Now, this is not the only answer. The period has to be 6. So that's going to be 0. This is going to be 6. And judging if it's a sinusoidal function that I try to draw for you, a lot of you actually can tell me what this number is going to be. That's going to be probably 3. And if we were to keep this pattern going, that's why a lot of you actually understand this. And I'm going to just choose a different color so you guys can see. The pattern should be the same. Now, I apologize, I'm using a tablet. But my question is, what's going to be this end value going to be? And a lot of you understand this. If this pattern's periodic, the pattern should repeat. So that should be 12, right? Because the period is 6. And a lot of you actually understand, what's this value going to be? So that has to be 9. And again, if you need some help to figure this out, this is a rough formula. Question 3 is a thinking problem. And just to help some people out with this very first question, a lot of students always get trouble with this. Given a periodic function, f of x with a period of 12, if f of 7 equals negative 2 and f of 11 equals 9, determine the value of f at 43. So all I'm going to do is give you guys a hint. Plot it out. Visualize what's happening. Notice they're telling you at f at 7, that value is at negative 2. So negative 2 is plotted down there. And f at 11, where's 11? 11 could be up here. And that has a value way up at 9. And I'm drawing into the map, but I apologize. So what's going to be the pattern? So basically, the period is 12. So honestly, if you keep on subtracting 43 minus 12, keep on subtracting, keep on subtracting, keep on subtracting, eventually you're going to either get 11 or a 7. And if you keep on repeating, subtracting, let's just do this one really quickly. So 43 minus 12, I think everyone agrees that's 31. That's not one of the answers, so keep on going, subtracting 12. 31 minus 12, well, that's 9. And that's, what did I, 2 minus 1 is 19. And then minus that 12 again. Oops, see, I'm running out of room. 19 minus 12, 7. So this answer is probably going to be that pattern that's going to be a negative 2. So obviously, we don't have any other information. We have no idea what the pattern looks like. Maybe it looks something weird like this, right? But who cares? It's saying that it's a periodic function. So all you have to do is basically subtract multitudes of 12, and you should get that answer. Question 4 and 5, you should be able to do yourself. And notice, we do have some references in your textbook that might assist you in case you found this video go tiresome. So we're going to the second handout, and I do apologize, the videos are already long. We're almost done, seriously, another 5 minutes or so. This is the trigonometric functions part 2. That's the first part of the graph. As you can see on your handout, now that you have it a digital copy, PDF, you can clearly see the colors, what I was trying to do, unraveling that unit circle, and that's the sine graph. The second one is the cosine graph. And again, it's the unravelment on its side. So that's why it starts at a maximum of 1. The tangent graph, we're really not going to look at, but it is actually a periodic phenomena, but it is not sinusoidal. So although we would like you to master it, again, it doesn't have any maximum, it doesn't have any minimums. You might want to think about what I just said there. So don't worry about these links. Don't worry about this triangle here. So I'll just write here, you can omit. It's helpful to kind of learn though, especially for the circular motions, and feel free to look online, animated GIFs, animated GIF, unit circle, or y equals sine x, online. And notice, those are the graphs. So you've actually already done this already, so I do encourage you can try to do it again. What does VA stand for? Vertical asymptotes. I already know that from before. And so we're just rinsing and repeating this exact same pattern. Again, you can answer these questions yourself. There's a couple things that you can also do is look at the symmetry. And again, notice the answers here. And again, this is actually the correct way of actually articulating those patterns that repeat at nice intervals for the x-intercepts. Finally, notice we have the graphs here on the last page, the radian measures. And again, it's exactly the same. However, just to make sure we're clear, and hopefully I'm emphasizing, what you need to know is these two graphs for sure, the sine graph and the cosine graph. There's clearly some other exercises, and you can actually try these yourselves. But basically what I was trying to get across to her today is the introduction or reintroduction for the y equals sine x, y equals cos x, or the periodic phenomena. I hope you had a good day, and I hope you find yourself all right. Please feel free to email me at any time, and I hope to see you in the future with the next video coming up. Bye for now.